All right, so welcome back. Welcome back to this video. So yeah, I haven't been making videos for like 4 days. So you know, there are some things that I have to like participate on. So sorry for the delay, but in this video we're going to like implement stable diffusion from scratch in Python. So we'll be going through like the code. So we'll be using PyTorch for this implementation. For this implementation, we're going to use like PyTorch. You know, so let's get started. So these are the two main files that I have used. So again, I have covered stable diffusion like in the past few videos. So we'll be going through that series. We'll be finishing that series. I'll also be covering some more advancements in stable diffusion. I'll try to cover some more papers or some more implementations. So we'll probably try to cover more. But in this video, we're going to implement it as I've just stated. So let's get started. First, so this is the file. I think so. This is we're going to go through this code, right? So this is the file in which we'll implement the diffusion part, right? We'll actually implement the training and the sampling part and the like addition of noise and all that. And in this file, in this model.py, we'll actually implement the model. So first, I think we'll first go through this one. We'll first go through DDPM file in which we'll implement like all of the like noising processes and all that, not the model, like all the processes that should be taking place while we implement stable diffusion. Again, remember stable diffusion, right? So we'll be taking an image or taking some random noise. So while training, we'll just have a training data set. We'll add some noise and we'll let the model predict the noise, what is added. And while in the inference type, we'll just give input the model with random noise, right? In the training, remember, as the training progresses, we'll add more and more noise. So the later the time steps, the more noise will be added. And we will of course reach a point in which there will be absolute noise and no image. So there will be like so much noise. We will reach a point like that, but let's get started. Right? So that is the idea of stable diffusion. In the inference time, we are going to input the model with complete noise, and the model will find some patterns or use the pre-trained knowledge that it has gained from training on the training dataset. We'll use that knowledge to actually predict images that look similar, right, to the images of the training distribution. So that is the idea. So these are the imports we'll be having in the DDPM library. We're going to import OS, Torch. We're going to import torch.nn to implement neural networks, matplotlib, TQDM, optimizer from Torch, right? We're also going to import like unit from this file. So we're going to import like from modules. So it's actually model. Right, from model, we're actually going to all right. So yeah. So let's start. Okay. So these are the imports we'll be importing. Say that. So these are the imports we'll be importing, and then we'll be first creating logs. We'll be creating logs throughout this code. So this is the class that we'll be building, the diffusion class that contains like almost all the functions that we'll be reading, right? So first, we'll create a diffusion class in which we're going to have the initialization function, in which we are going to import like bunch of parameters that we'll be needing, the noise steps, right? The number of steps. We're going to have like bunch of parameters. I'm going to talk through them as we go on. We'll have like image size and all that. So I'm going to initialize all of these values, right? So the beta parameter is going to be like, we're going to call this function prepare noise schedule on. We're going to call this function, and this output is going to be the output of beta. I'm going to go through that, what that is. And alpha is going to be nothing but the 1 minus all the values of beta. So it's going to be opposite to what the values of beta are. So we're going to have like a trade-off values, right? And then this is the function through which we'll create the beta. So in which we are going to create a linear space in which the parameter is going to be beta dot start, beta dot end, and noise steps. So in like this linear space, we're going to get all the linearly or equally spaced values, right? From this start to from this end, like these noise steps, we're going to get even values to actually. So why will we actually use it? We will use this beta value to define the noise as we go on through training. We're going to have like evenly spaced noises or evenly spaced values between this beta start and end values. So the start is this small value and end is this 0.02, right? And then we'll create this function noise images in which we are going to take x and the time step, right? We're going to get the square. We're going to just like create these formulas to actually calculate the alpha hat, and then we'll square root it. And there's a bunch of details around this. I will cover that in the future videos of stable diffusion. Remember, we're just starting off, right? And then so this is the noise. So this is the noise. So what we'll be taking is we'll be taking x and t, the current like number of training steps. What we'll be doing is after like calculating all of this, right? We'll be calculating square root of like that current alpha value. So we're going to have like bunch of alpha values, right? So alpha is going so beta is actually going to be evenly spaced values, and alpha is going to be 1 minus that. So it is going to be the same number. We're going to get the square root of that position, right? And then I'm going to 1 minus alpha hat. I'm going to calculate square root of 1 minus alpha hat. I'm just going to get the 1 minus this value. I'm going to square that or square root that, and then we'll calculate the epsilon, which is the noise, right? Just random noise. And then we're going to multiply that by we're going to multiply x, right? So we're going to take an x, we're going to take x and multiply that by this value, square root alpha hat, right? We're going to just multiply these values, just like scale it. And then we're also going to multiply the square root 1 minus alpha hat with epsilon, right? So we're going to have this 1 minus alpha hat value with epsilon. So essentially, we are using this alpha hat and 1 minus alpha hat to control how much noise we should add for that specific time step. So we're going to have like multiple time step, and each time step we're going to call this function. And as time step uh, increases, as we go on through time step, as time step increases, we are going to give more priority to this factor or to this term, right? To this term, square root 1 minus alpha hat times epsilon. That is, we're going to add more and more noise as time step goes on. And then as so that is the idea. We're going to get the values and all that. So it kind of seems intuitive. I don't even have to explain it. So alpha hat values is going to be evenly spaced values, and we're going to get the square root of them. And the bigger this value, the smaller this value is, and we're going to have like a trade-off between the amount of image should be present and the amount of noise that should be like included in that. So that is the idea of this function, noise images. And then the sample time steps, in which we'll just take in n. I we'll cover that after. And this is the main function, sample function, and in which we'll take model and n, the number of I think that the number of images we want to predict. So this is actually for generating that images. So we'll take the model and the number of images we want. So this is going to be like image integer, specifying the number of images we want to generate, not an integer, a whole number, right? And then I'm going to like create a log. We're going to create a logging. We're going to create a log, and then we'll just create some random noise, because we want to pass that random noise to the model, right? As like through the number of time steps, right? I'm going to create a for loop that loops through the number of time steps, right? Essentially, we'll be reversing this like noise steps, self-drop noise steps. So I think self-drop noise steps is just going to be noise steps, all of the noise steps. That will be like I think it will be a parameter. So it currently it is 1000. It is set to 1000, right? And then we're gonna have the image size by 3. So that we are just going to create like random vectors or random matrices before the for loop, and then I'm going to loop through this. I'm going to loop through one through. I'm going to loop from 1 to 1,000, right? I'm going to calculate t, which is going to be like a bunch of ones. So we are essentially going to get a bunch of ones. I'm going to predict the noise. I'm going to pass this t and x. I'm going to taking this random noise x and the t, right? I have to pass both of these values into model, right? And then so essentially this t is actually going to be the time step. So as you can see, we're going to get the events and multiply that by I. So I is actually going to be the index value or the iterating value that is going to increase as the loop goes on, right? So this is going to be we're just going to multiply that. So it is going to be a the time step. We're going to pass the time step and the noise to the model and get the predicted noise, what the predicted noise is, right? And then I'm going to get the alpha. I'm going to calculate, I'm going to get the alpha, the current alpha hat, and the current beta. I'm going to get all these values. I'm going to say if I is equal to 1, right? If so, as you can see, we are going to use a reverse function here, right? If we are in the last iteration, if we are in the last iteration, or if we are not in the last iteration, right? If we are not in the last time step, we are going to like create this noise. We are going to create this noise. If not, if we are in the last, if we are in the last iteration, we are just going to specify the noise to be zeros, such that we don't affect the the final output. Like it doesn't make sense. And then we'll use this formula to actually get this final x. We'll calculate the final x to this model for our formula, in which we'll just have this. We'll square root alpha, multiply that by x into 1 minus alpha by all these things, right? Notice the predicted noise. Like you can just notice the presence of all of these things that we have just calculated above. Beta, noise, this random noise, and the predicted noise. So essentially I'm going to I mean, yeah, I'll cover this in the future videos. So, you could just go through this if you want to. Like, if you just put, like, get a calculator and all that, you can try with all of the different values. That will be very helpful. And then we could actually call the train function to actually train the model. And then I'll also like C lamp the values. So C lamp is actually used to um, like make the values into a specific range. We are going to make the values into -1, 1. So all the values are going to be in the range of -1 and 1, right? And then I'm going to like multiply that by 255. So I'm going to essentially I'm going to have values from 255, and then I'm going to return x. So this is the formulas. So this is the process that will be happening in the sample function. We'll take in the model and we'll take in the number of images we want to predict, and then we'll create a random noise, x, right? And then we're going to update x, as you can see here. We're going to update x as we go on, right? And then like, yeah, we're going to loop through the time steps in the reverse order from, let's say, from one. Let's say we have 1,000 noise steps. We are going to loop from 199, or we are going to loop from 99 or 999 to 1 when the reverse order, right? I'm going to get the t, right? T is actually essentially going to be a time step. We're going to pass this t and x to the model. I'm going to calculate that. I'm going to get the current alpha value, the current alpha hat value, the beta value, and the noise. And then we'll just calculate this to actually get this, to actually update this x value. And then we'll perform this again and again on x value, right? We'll perform this function, all these functions on x value, and we're going to get we're going to update x value as we go on through the number of time steps. And then I'm going to perform these values on x, and I'm going to return x. Right? Hopefully you understand what is going on here. And then now we can actually build the train function. actually train this model, right? I'm going to do a bunch of things here. I'm going to set the login and all that. We're going to create the unit. So unit is actually a class from this file that we are going to import in just a minute. So don't worry, right? We are going to use the MSE loss, right? We are going to use the MSE loss between the actual noise and predicted noise. We are going to use the diffusion. Where is diffusion? Where we have imported? Yeah. So we are going to have, we are going to employ. We are going to create an object of this class that we have built here above with all these functions. Right. I'm going to create like another long function. So this is the main training loop. This is the main training loop. We'll go loop through arcs.epoch. So we're going to have like argument of epochs, the number of epochs we want to train the model on, right? And then we'll just loop through like this value on the, we're just going to loop through the data like for each data, right? And then so in each epoch we're going to get the data and we're going to loop through the data, and then we are going to perform this sample time steps. We're going to perform this function on the images.shape. We are going to pass the number of images. We are going to pass the number of images through this sample time steps, and let's get like a random integer of like we're going to get a random integer from 1 to 1000 or 1 to the number of noise steps, right? And then right, we're going to get this sample time steps. We're going to noise the images. We're going to create the noise images, right? We're going to add noises to these images, and we're going to pass the time step also. So we're going to perform this function, right? We're going to calculate the noise and add the noise based on the time step. So the higher the time step, the higher the noise values. And then we're going to predict the noise from the model. We're going to call this model of unit. We're going to pass in the this value and the t value, the current time step value. And we're going to calculate the MSE loss between this noise and this predicted noise, right? Understand, right? So again, here we are going to like return epsilon here just to make sure that we get the y value, and we could actually compare the predicted and the actual noise. And then yeah, we are going to get the loss, the MSE, and then we could actually train the model using optimizer.0grad. We're going to say a loss.backward and optimizer step, and then we can actually train the model, right? And then this we could after training or like after looping through all these images, we could actually carry this sample. We could actually sample these images, or we could actually predict on these images, right? We could actually use these images to predict on other images, right? We could actually sample this model on we could or not on other images. We could use this model to predict images. So after like at training, right? At training, after each step, after each epoch, we are going to use this model. We are going to test the model by actually predicting new images just to see how it performs. We're going to sample it at each epoch, right? I'm going to save these images, and we're going to save the model as a checkpoint. And this is the first file, and we'll very fast go through the second file. So in the second file, we'll have the model, the implementation details. I'm going to go through it very fastly because we are pretty comfortable with almost all of these functions that we'll be using here. In this implementation, however, we're going to use the self-attention, right? We're going to use self-attention mechanism. So self-attention is essentially so I hope you know about attention mechanism. So it is a mechanism that is used behind ChatGPT also to actually understand the relation between the words. So attention mechanism. We're going to use the same mechanism in stable diffusion to generate images, but we're going to use self-attention. That is the image, right? We're going to divide this image into like 3 parts, and then we're going to calculate the attention between these 3 parts. All right, we're going to make the model aware of this relation between this we are going to make the model aware of different parts of these images such that model can understand what is happening between these different parts. You get the idea, right? We're going to build the self attention. I'm going to go through that I'm going to talk about that as we go on further. We're going to do the classic attention. We're going to get the multi-head attention function from touch. Right? I'm going to create a feed forward neural network at the to calculate it at the output. So this is the forward function. So here, see what we'll do. We'll take an x. X is going to be, let's say, the image or some output. We're going to divide this into like 3 parts, or we're going to divide that through channels, or we're going to divide the channels, and then I'm going to pass this x through a linear layer, or we're going to normalize this x, right? We're going to normalize this x, not linear layer. We're going to pass this x through a normalization layer. We're going to normalize this x layer value, and we're going to pass the same value x normalized x 3 times into this multi-head attention. So we're essentially going to calculate how this x normalized values, or we're going to calculate how this xln is or how much attention this has to pay to different parts of this xln. So essentially it can the model will understand this image better by understanding the relations, and get more context and get more understanding of that particular value, right? I'm going to calculate the residual layer. I'm going to add the attention value with x, the actual value. I'm going to pass this attention value through the attention layer, or through this feed forward layer, through this or defined neural network. We're going to calculate the normalization linear layer, and we're going to use a new activation function called GLU, and then we're going to pass that through an output linear layer. And then we're going to pass this attention value through this neural network, and then we're going to add the residual value of the previous attention value, and then we could actually output this value after reshaping it, right? So that is the idea of self attention, that is the implementation of self attention. And then we're going to have a double convolution layer, double convolution in which we will just group like a lot of functions. We'll have like residual, we are just going to create blocks that we can use again and again. We're going to have like convolution 2D layer, group normalization layer, another convolution 2D layer, and then if self dot residual is true, then I'm going to add the residual. If not, we are not going to add. So that is the we are going to create bunch of residual blocks that we can add upon to actually build the model, right? So this is the double convolution layer or double convolution block. So this is the down block, and we are going to use the unit, right? We're going to have the upscaling layer and downscaling layer. So this is the downscaling layer, in which you're going to use this double convolution block that we have defined above. We're going to use it a bunch of times, and then we're going to use max pooling, right? We're going to max pool, pass that through double convolution layer. We're going to have an embedding layer, right? We're going to use this activation function, right? And then the linear, so the output is actually going to be this even linear layer, which is going to be the embedding dimension by output channels to actually get the embeddings. So this is the forward function, in which we'll have we'll calculate this maximal convolution layer or maximal convolution neural network, and then we're going to calculate the embedding. We're going to pass that through the embedding layer, and then we're essentially going to reshape it to the required size, and we're going to add both of this x and the embedding. And this is the upward. So this is the upward layer, right? In which so we're going to have the upward and the downward, right? So first we're going to have the downward and the upward. So this is the upsampling layer or upsampling block, right? And then first we're going to use nn.upsample to upsample this that image or that previous vector, hidden vector. We are going to pass that through this neural network. So we're going to create this neural network, right? In which you're going to have 2 double convolution layers. and this is the embedding layer. Similar to the below the previous implementation. We're going to have the forward function, which takes in x, skip x, and t. We're going to upsample x, and then we're going to concatenate skip x and x. We're going to pass this x to the CNN layer. We're going to calculate the embedding and add the x and embedding. So that is the both the up and down layers. And then again, we're going to import like bunch of these layers. You can just go through this details. So we are also going to import we are also going to include positional encoding just to make sure the model is aware of the positions. It can understand positions of like each value, right? And this is the forward layer, in which we're going to have we're going to unsqueeze it, positional encoding. We're going to perform this INC, a double convolution layer. We're going to perform down sampling layer 1, first down sampling layer. We're going to perform self attention layer, down sampling layer 2, self attention 2, down 3, self and 3, and you can definitely add as many layers as you want, like for different types. And we're going to have we're going to perform like a bunch of double convolution layers. We're going to create a bunch of double convolutional blocks that we have built previously. And then this is the upsampling layer, in which we are going to upsample it. We're going to perform self-attention again, upsample it, self-attention again, upsample, self-attention, and get the output. And remember, we could perform self-attention. There is no problem, because remember, whenever there is weights and whenever there is gradients, right? Whenever whenever there is a model that can understand data better, even though it is not directly linked with the even though it is not the intuitively, even though it doesn't make sense intuitively, whenever there is something that makes the model understand the data better, definitely use it. So self-attention is actually a very good way for us to make the model better understand the data itself, even though it is like only one data, right? One group of data. By self-attention, we could actually make the model understand the data better, right? Get different features and give more importance to specific features and neglect the other ones. So that is the idea. And then we can just get this output. So this is the implementation. This is the implementation of stable diffusion. Hope you understand what's going on here. So thank you for staying with me. Thank you for watching this. So I'll see you in the next video.